that may sound pretty slow to you, but when you consider that, like a bacterial cell, like an E. coli or something like that, might be 1,000 nanometers or 1 micron in diameter. So that's saying that if you tracked one lipid molecule, in a second or two, it might have moved all the way around the cell. Protein molecules, an order of magnitude slower than that, maybe 20 times slower than that. It depends on how big they are. These guys move quickly because they're much smaller than the proteins. And diffusion is related to, diffusion rates are related to.
So they're just
size.
wired and they're just moving across the top of the,
They're moving through this,
yeah.
as think of this as a two-dimensional solvent, and they're just floating around in here.
But they're not, like that integral protein is floating around, but you couldn't just pull it out. It's,
No, not easily.
but it's still moving.
Yeah. It's like a big old oil tanker floating around in this sea of lipids. The lipids are moving much faster than it is. The bigger the protein, the slower it goes. Okay. These systems are asymmetric, which just means they're not mirror images of each other. And we've seen that already. There's asymmetry when you compare the outer leaflet to the inner leaflet. We can see carbohydrates on one side, not on the other. That's a kind of asymmetry. Turns out there's asymmetry in the kinds of proteins too, and in the kinds of lipids lipids on the outside versus the inside. So we talk about symmetry both in terms of lateral and transverse. Transverse means across the membrane, so transverse would be outside versus inside. Lateral just means within the plane. So even within the plane, the lipids aren't all the same. So what I'm saying is that the pictures we've shown don't give you that picture. This is a lie, in other words. Yes?
You said transverse was